All right. Good afternoon, ladies and gentlemen. So today I'm going to discuss how I've been creating mathematical abstractions. I'm instructor Anthony. This is the Morsiglio School of Wisdom, where inspiration meets intuition. So the purpose of this discussion is to give insight into how I'm able to generate these abstractions. You can also utilize the tools that I use to generate your abstractions if you wish. So I figured, why keep the knowledge to myself when I could share it with you? So I'll be using three tools. GitHub is where I'm going to store most of my code that I am running for the applications. Overleaf is an online compiler that uses mathematical notation. And lastly is MATLAB. MATLAB is a matrix laboratory. It is scientific computing software. If you're not familiar with MATLAB, then it might be beneficial to run through a few tutorials online before using it. So, because what I'm going to share, it requires some fundamental knowledge on mathematics, such as calculus, pre-calculus, and trigonometry, and a little bit of algebra, then I strongly suggest that you brush up your skills if it's been a long time since your math skills, and you may participate in this endeavor. So without further ado, let's start off with the code. Okay, so the main code that I'm using to run and obtain the abstractions is PC map. It's the primary function. So the first thing that I'm going to do is generate a set of complex numbers. So let's recall that every complex number has a real and imaginary part. So if Z is a complex number, this is the set of all complex numbers. So we're just taking one complex number. It can be expressed as A plus IB, where A and B are real numbers, and I squared is equal to -1. Every complex number has a modulus or a radius. This is obtained by taking the square root and then A squared plus B squared. And it will be greater than or equal to 0. The angle is the arctangent or the inverse tangent of B divided by A. So let's recall we can use Euler's formula to represent any complex number in terms of its radius and its angle, where the radius is the modulus and the angle is obtained previously. Okay, so what's interesting is we can iterate over a collection of complex numbers. Let's take a collection of n by n complex values on a grid. Each value can be assigned a unique pair of real numbers, A and B. Then we can assign a unique identifier on the lattice to generate a sequence. What we mean here is every complex number has a unique pair of coordinates, A and B. So if we have n, capital N, components in A, A1, A2 through AN, and similarly for B, B1, B2 through Bn, then we have Z, Z1, Z2 through Zn. There are n complex numbers. Okay, so we're going to take capital Z as x plus I times y, where x and y are a collection of n real numbers. Now, capital Z is a mesh grid consisting of two lattices, or linear, or distinct real numbers each. So we have a total of 2n real numbers. So in mathematics, we say we can generate a map that's bijective from one set, which is R2, onto the complex numbers. But since we have n real numbers, we're generating a map from R2n to Cn. Okay, now we have a mesh grid on values of x and y. So we can generate random variables. Why do we do this? We generate random variables to obtain random values, A1, A2 through AN. Now we'll use different probability distribution functions to obtain those random values, and they have a specific structure to them. So we're going to consider the simplest probability distribution function, and it is referred to as the uniform distribution. So Let's take capital X and capital Y as a collection of identically independent distributed and uniform random variables between A and B. A is less than B, and A and B are real numbers. Now, we can also take this as a different distribution. For instance, normal distribution, binomial distribution, Poisson distribution, hypergeometric, geometric, exponential distribution. There are plenty of distributions that are used in the sciences. But we're just considering the simplest case. Okay, the next step is we're going to generate a function that depends on each of those real values, X and Y. And because we have a total of n X components and n Y components, then we have 2n in total here. All right, so this is a set of n values, this W, because it's a function map. Ideally, we want to take W as non-negative, so we can just take the absolute value. Now we're going to just iterate, and we'll obtain the finalized result. All right, let's take a look at the code. The first thing we're going to do is open up a figure. We're going to remove the grid, turn off the axis, simulate random variables between -1 and 1. We'll generate a random complex variable. This is used to increase the dispersivity of the RGB scale. Increasing this value will increase the spectrum. If you want a more compact spectrum, it is ideal to use a number smaller. So if I take this to be 100, then it's not going to look the same as 10. The next is the number of iterations. You can think of this as the pixelated resolution on your television or computer. Okay. The next is we're going to scale the magnitude of the bounds on the X and the Y components. And we're going to normalize the random variable, the bounds. We'll generate a sequence of linearly spaced points between lower bound, upper bound, and the total number of M values to generate a mesh grid here on the complex plane. So because the Cn is bijective to Rn by Rn, where Rn is on capital X and Y is Rn as well. Okay, the next thing we're going to do is generate a grid of those complex values. So I'll make a comment. This little m, it should be integer, positive. But the lower bound and the upper bound of X and Y can be any real number, as long as the lower bound is less than the upper bound. Okay, we're going to iterate over COL. This is an integer as well. We took it as a random integer between 1 and 15. We're going to apply a perturbation onto the value of the complex number, and we're going to take a function of X and Y. Let's recall that Z is expressed in terms of X plus I times Y on the mesh grid. So this is a function of X and Y. I choose to use the exponential function because it's not negative. I'm using a negative for exponential decay. So greater values of this inside argument will lead to reduced values in W. And we have something periodic, a trigonometric function. It is the combination of non-negativity, periodicity, that will give rise to interesting phenomena. Lastly, we take a pseudo color grid on the values of W. And let's remember that we can normalize between 0 and 1 if necessary. And we'll apply interpolated shading on the map. Okay, the last thing to do is to choose a color map. Any map will do. So I'm using a custom color map here. So we can choose different values of RGB spectrum. And N is the number of iterates on the RGB. This is a matrix. It is N by 3, where 3 is the columns, and capital N is the number of rows. Okay. So this is one of the default color maps, hot. There are other maps as well, such as winter, summer, think autumn or fall. And let's say copper or bone. So we can take bone without loss of generality. It should be fine. And we'll change the GCA color to white, or you can use black, which is in K. All right, so this is the code. Let's run it. So this, I have a comment. This code, there's the primary version, PC map, and there's the iterative version, PC map loop with capital N. Capital N is the number of iterations that will run PC map. Every time we run this, for each value between 1 and capital N, where capital N is integer, 1, 2, 3, 4, 5, etc., then we will run PC map each time. The reason why we do this is it gives us a greater level of flexibility and spontaneity. All right, so let's run it for a total of 5 times. This is my personal GitHub. I've run some elementary computations during my previous studies, and I use it for personal projects as well. This is my most recent project. It consists of an overleaf template and the previous .m files. The .m files are MATLAB files for Matrix Laboratory. You can download them if you have MATLAB on your local desktop or at your local institution, and you can run them yourselves. Okay, let's take a look at the overleaf. Now we have the following. We generate a title and we start with the first section. This is your first mathematical abstraction that you can use. So this is a sample. I named it foci concentrici, which means it's in Italian, center foci. Okay, now here, let's take a look. So we can use the plus to increase the zoom. We have fxy equals to exponential function -1 divided by cosine z. So if you are not familiar with this notation, please do not use it. All this says is a and b are real numbers, and I squared is equal to -1. And this function in x and y is a function here. Z is equal to x plus iy, as we saw previously. The next thing is the probability distribution function. So we're taking a and b to be uniform between 0 and 1. And lastly is the signature. Let's take a look to the left. FRC is the default font that I'm using for the signature. So for giggles, we're using Leonardo da Vinci because Da Vinci was very intelligent. And if you take a look at his work, it's phenomenal. But he did not use scientific computations and computers. He used his bare hands. So, but his IQ was off the charts. Everyone knows about Da Vinci. He was an Italian scientist during the Renaissance. Okay. The next is the title. So the title is Foci concentrici. This is the foci, centered foci. Okay. You can insert your quotation. The quotation is something that you wish to send a message to your audience. I like to utilize quotations that are a reflection of my culture and what I am thinking about in the meantime. So for me, my culture resides in Italian, meaning that I have ethnicity that reigns in the Renaissance. So I wish to preserve my culture. So I'm utilizing the Italian language. Okay. Lastly, we will upload a figure. The figure can be in JPEG form, or it can be in PNG or PDF. As long as this matches on the left-hand side, then we should be able to compile. Okay, so let's come back to our code. All right, so after compiling, we have the following. This is the first figure. This is the second figure. This is the third figure. This is the fourth figure. And this is the fifth figure. Let's use the fourth figure. Let's create our axis. All right, as you can see, little m is 2,500. So we have 2,500 by 2,500 iterates on the lattice grid. Each point has an associated RGB value that gives its rise to color. So as you can see, it's a continuous spectrum. We discretize the lattice grid in terms of 2,500 by 2,500 points. And by increasing the resolution, i.e. by increasing the number of points, we can generate an increased detail of the picture. So this region looks interesting. So I'm going to set the limits on the x-axis between 0 and 1,000. Okay. Now I'm going to constrict the y-axis between 500 and 2,000. Now, this looks pretty interesting. The only thing I'm going to say is the distance between the center of the dense region, which has the darker saturation, is not the same towards the bounds here. They're not equidistant. And if we wish to preserve symmetry, we need them to be close to equidistant. So the first thing I'm going to do is I'm going to look towards the center here. We see the y value is 1389. I'm going to take an approximation at 1375, and I'm going to add 500 and subtract 500. This looks much closer. I think this is as close as we can get. So now I'm going to erase the axis. All right. And lastly, I'm going to export the finalized results in terms of PDF. We can use PDF or we can use PNG or JPEG. Let's see how it looks if we have black as our GCF. I think this looks a little bit better. Let's use black instead of white. Let's use a different value. Test 2. Okay, this is my process of creating these abstractions. So if you wish to find a different pattern, then you need to use a different function, or a different probability distribution function, or different bounds, or different number of resolutions. There are many different elements that we can put into the melting pot to get a different finalized result. Okay, so now I'm going to insert the previous picture that I just created. All right, the next step is to crop out this excess material here. We can see there's a clear discrete difference between this region and this region here. All right, so that's the first step. That looks almost good. There's a little bit of black at the top. Let's try again. That should be good. Oh, I need a little bit more to the right. And a little bit higher. Okay. The symmetry isn't perfect. We can see that there's a difference here in this region as compared to here. But this is due to the abstraction that the function is created, not due our user error. So it is okay. All right, the next step that I'm going to do is I'm going to resize this. And we're going to generate a tessellation to a degree, because we're not starting from the basic structures of geometry. All right, we can customize this in format picture. And we can create a rotation. Okay, so I'm going to tell you how I think when I generate my abstractions. The first thing is we see there's a higher region of saturation towards the center and towards the left. And towards the right, we see a higher heterogeneity in terms of its pixelations. So what I'm going to do is think about how I want my audience to perceive the figure. Now, for simplicity, we can focus all this, we can choose the heterogeneity towards the outside, which will help the audience to think outside of the box and more abstractly. If we want the audience to focus towards the center, I will keep these pixelations towards the center. I'll show you two ways of doing this. So the first method I will do first. All right. This is what we are interested in. Now, earlier in some of my simulations that I've run, we saw a distinct color. So there's a lighting. One is darker and the other is lighter. So how do we correct this? Just 1 second. Okay, so it's under 3D format, and then it's in lighting. Okay, I think the most ideal case is flat. This should give us what we want. So now we can see there's a clear continuous distribution here. So now this method will help the audience to think starting from the center outside. So let's consider the opposite. All right. So now I'm going to focus the center towards here. So we see that there are two different methods to which we can obtain an abstraction. We can also increase the number of pixelations by copying and pasting. Let's rotate it 90 degrees. Okay, I don't like it. So sometimes you just have to play with it and see what you can obtain. So this is abstract, meaning that it's not for everyone. So if you're not particularly fond of this methodology, you are more than welcome to utilize your own methods. But I figured I would share with you how I've been doing it myself. All right, what's the next step? Okay, the next step is we're going to put our signature on it and the message we wish to convey. Let's call it, let's think of a name. I don't know. Let's call it duality. It doesn't make much sense, but this is just for a test. Okay. This function here must match what we have in the code. It's very important. Theoretically, you can use different functions and combine them into one figure. As long as you use one of the functions that are utilized in your generation, I don't think you need to include all of them, but please at least include one of them. All right. So this is our function, exp negative absolute value 1 over cosine z. So the absolute value of 1 is just 1, so it just distributes. And then we have divided by absolute value cosine z. Okay. So now let's customize. So this one is written by Da Vinci. Of course, I don't think Da Vinci would actually write this, but it's just for fun. All right. So I'm going to snip this, and typically I like to put the title and the quotation or the message towards the center and the signature on the side. If you're not familiar with the mathematical notation and you want to make sure that you don't use the incorrect one, you don't have to use it. All right. So you may be wondering, what's exactly these symbols here? They're just different symbols that are translated in overleaf. And so each letter of Leonardo da Vinci's name is translated into these collection of symbols. It has absolutely no meaning, but it looks cool. So I like it. I think that would be all right. And what I'm going to do is I'm going to generate a border around this here. We can, now the next thing I'm going to do is I need to combine these two. So these two need to be combined. We may need to try a couple times before getting the right one. Just 1 second. Sorry. Okay. I'm going to replace these two with the new snip figure. All right. Now I'm going to place a border around this one. We can change and use something else, something that is more refined. For simplicity, though, I like to keep it very similar. This one should be fine. You have a shadow too. All right. The next thing is we need the function. Again, this is optional. You do not need to use the function if you're not familiar with it. Oh, that one doesn't look that good. So I'm not going to make this as perfect as possible because this is only a tutorial. So sometimes it depends how lucky you get, but you can get some pretty nice figures. So there's a little bit of luck, but there's also some creativity on your end as well. All right, we're going to add a border here. Okay, the last thing we need is we need the title and the message. I need to recompile this. So I'll make a comment. When you change the code on the left-hand side, the right-hand side will not change. It's not like Word. You have to recompile before it can change. Also, I'm going to update the new figure that we're using. Test 2. And then this should change. All right. So now you can see this is the figure that we're using. And the last thing that we need is the message. An agile heart gives rise to a quick mind, something like this. should be placed towards the center. This is fine. Okay. And the title is duality. This would make more sense if you've seen me use different color maps. So I'm going to show you some of the techniques that I've used. This is probably going a little bit over time, but it's fine. All right, and we need to place borders on this one. I'm not sure why this one is thick. It should be thinner. There we go. And lastly, I'm going to center this. Okay. The last step, we can change this. So sometimes I do this step before the next step. So I'm just going to make a duplicate. Now, what I can do is change the artistic effects here. This is very simple. So I'm not sure how PowerPoint does this, but it's very useful for increasing the amount of freedom that the user has in generating the figure. So we can get some pretty interesting things. This one, I don't like it. This one I like, plastic wrap. This one is a bit weird. So it depends on the saturation of the RGB color scale. But then we also have glass bubbles. That one doesn't look that good either. Blur, cement, photocopy. Glow is cool. I like glow. All right, I think this is what we're going to use. Because as you can see, the blur is towards the outside and it focuses the audience's attention towards the center. So we can see there's something interesting towards the center. All right, I think this is what we want. So the last thing we're going to do is once we generate effects, which is optional, you don't have to, but if you wish, you can. And now I'm going to snip. Okay. And I'm going to create a new slide, copy and paste. And now I'm going to create a reflection. So I size and position, and then I generate reflection. Sorry, it should be this one, format picture. Here, that's it. So we just finished something different. And this one, it's taking up most. And now we just save it. This one is by Da Vinci. So I need to actually change this a little bit. I don't have enough space because of the zoom. I think that should be enough. Okay. Yes, perfect. The only thing I see is this is taking, the shadow is taking this. The reflection is taking this, which I don't want. So I'm going to change this just slightly. So I need to decrease the length of the shadow. I think that's good enough. Let's try 62. 62 is good, or 3. 3 is good. Okay. This is what I want. All right. So now I think we just got ourselves a figure. That's it. So you can try yourself and see what you get. You can share using hashtag mathematical abstraction design. So let's say hashtag mathematical and we'll save it there. This is the finalized result. All right, so you may be seeing I've been getting some interesting figures. So there's another thing we can do, and I'll share that too. So what I like to utilize is something referred to as dichotomy and contrast. And these are principles used in, for instance, Taoism, yin and yang. So this is tranquil, we can see. It makes us feel calm, but also bewildered. So if I'm going to think of something that makes me more intense and upbeat or passionate and excited, I probably want to utilize the color of red. You see this utilized in many different corporations that try and elicit a sense of passion from their target audience. Okay, so this is the one, HOT. I'm going to use that map to convey that feeling. All right, so color map, and then hot is all I do. Now I check my figure. Voila, we got a new idea. And that's how we create the abstraction. So now when I save it, actually I want to export it. If we wish to preserve symmetry, the idea is to use the exact same. I can just change it to white just to see what we get. If we really want to see a mirror reflection. I like it better in black. That looks cooler. All right. So now I'm just going to change this to the color scale that was used, HOT. All right, so now I go back to my PowerPoint. And now I can't change this entire image. But what I can do is, because I still have this one, I can duplicate it. Now I can change this from device. And I'm going to use the new one that has the dichotomy, which is this. As you can see, this preserves all of the transformations, the rotation, the reflection, which is very ideal in PowerPoint. I'm actually a big fan. Okay, the next thing is I'm going to crop this so that we can remove the excess black. Okay, there's still a little bit too much on top. All right. And lastly, this needs to be the same here. Let's see if we can get a good fit. Close. I think that's pretty close. All right. So now I'm just going to, oh, this one we see is, do I want to do it this way? I think it would be better. Okay. Just 1 second. Oh, I didn't create a copy of this. Oh, I know what I can do. Yes, I'll just do this. Control Z. Yes, that's what I want. Okay. Now that looks pretty cool if you're asking me. This one is, think about it. How does it make you feel? It makes you think of both good and bad, but there is similarity between them towards the center, neutral, right? So there's both good and bad and good. But when both are balanced, we have neutral. Okay. So now what I'm going to do is I'm going to copy this. This is decent. Okay. So it depends on how I want to convey the message, what colors I choose. It has a meaning. And this I can change. So this is why we created a copy, because just in case I wanted to change something. So I don't keep all the steps in my finalized gallery, but I choose to have them step by step in this default PowerPoint. Now, all I need to do is replace this with the copied image, which is on the snip. That's it. So now I got something new. I would say that this should be in red so that it can match this, but I could just change this to the other side and then we should be all right. So I'll do that. And this needs to be rotated. Okay. All right, so I think I would need to copy this and then create this image again. But I think this is sufficient. So let's just say version 2. I won't do a reflection on this one. So this one is dichotomous. Let's say V2. This one actually came out, I think, better towards the center. It makes the audience think about good versus bad. So I'm a big fan of dichotomy and Taoism. So I like these principles. Okay, and this one makes more sense with the title. That's actually why I chose to create a copy so that we can have the dichotomous structure, because duality and dichotomy are similar. An agile heart gives rise to a quick mind. This quotation makes no sense, but it looks cool. So this is how I've been doing what I've been doing. If you've enjoyed this, please let me know. I'll continue. If you think it's silly and a waste of time, you can let me know too, and I'll just work on something else. But so this is what I taught today. So I hope you'd enjoy it, and I guess you can support me if you like it. If you don't, then I don't know. You can do what you like. So, but I find this to be very fun, and I like what I'm able to generate using the tools that I've learned previously. So I figured I'd share it, because what's the point of keeping the knowledge to myself? So that will conclude this lecture, and I hope you have a great day.